Okay, and I have to, oh, there you go. So yes, exciting. There you go. Okay. And I have to,
all right, is it 3 o'clock or should I wait?
One more minute.
One more minute. All right. All right, I think it's 3 o'clock, so let's get started and not make everyone wait too long. So welcome everyone to this 31st installment in this year of the NC State Source to Sync webinar series, generously co-sponsored by NSF, NC State University, LSU, SKLEC in Shanghai, and Utrecht University, where I'm at. So I'm very happy to have Juan Paniagua-Arroyave, or Pani, for his colleagues and friends here today with us. But before I introduce Pani, first, to all of you that are new here, there are 120 talks now online in this seminar series that you can find on the YouTube link that is on the screen. And all talks are automatically streamed to YouTube and saved there for future generations. You can also follow Paul Liu on Twitter at Source2Sync to get the latest updates and new announcements, including next week's talk by Dongfeng Li from the National University in Singapore, talking about fluvial sediment fluxes in high mountain Asia. But as I said, for today, I'm very happy to have Pani with us. He's an associate professor at AFID University in Medellin, Colombia, where he's been for a couple of years now. He got his bachelor's and master's at that same university and then left for Florida to study under Peter Adams and look at the hydrodynamics and coastal geomorphology of Cape-related shoals on the east coast of the US. He graduated in 2018, and I was very lucky that he joined my lab at Florida State as a postdoc for a year before he went back to Columbia. Pani has wide-ranging interests into hydrodynamics and coastal geomorphology on coasts in general, but particularly in tropical coastlines. So I hope he'll talk a little bit about that as well today. So with that, Pani, if you could share your screen, I'll stop my share. And the floor is yours.
Okay, can you hear me well? Okay. And
I
you see my screen?
Yes, I still see a red screen, but I guess that's what I'm supposed to see.
Yes, that's part of the theater. So thank you very much for the invite. I'm very happy and very honored to be part of this series, because if you can have the chance to take a look at the other talks, you can see the level and the capacity, the knowledge that they can, the broad of the knowledge that they show. And for today, I have the pleasure to present some of the work that I have been doing with Yap in his lab. And the talk is going to be focused on how can we predict and the methods that we use to predict delta morphology from what we call the Gallo-way of predicting delta shape. And I have to say thank you to many people. Let me do this first. Okay. I have to say thank you to many people, especially Yap, of course, because this is in collaboration with him, but also people here at EAFIT, Juan Restrepo, and people at Colorado, Albert, of course, Francis at Utrecht, and the several students, bachelor's, master's, and doctoral students that I have had during these years at EAFIT, Julian, Esteban, Anderson, Juan Luis, Juanita, Alejandro, but also the other people that I work with in the estuarine realm, my professor Arnoldo, Lili, Vlado here at the University of Antioquia, Yulei, and Oscar. And with that, I also have to say thank you to the sponsors, the NSF, for a project that they awarded to YAP, Utrecht University, and Florida State University. And with that, I'll try to follow this outline, because I would like to talk about how we can predict delta shape within the Gallo-way framework. And with that, I'm gonna do a very quick overview of why do we care about predicting delta morphology. Then I'm gonna talk about this seminal work by Gallo-way on the delta shape and how it is framed within this triangle that everybody knows, roughly speaking, but also that has a lot of potential for what we can do with it. Then I'm gonna talk about how we calculate, how we quantify this framework. I'm gonna show some last I'm gonna show some applications of this method. So first, let's talk about why predicting delta morphology. And here, Professor Sivitsky provides a very nice, short, concise overview of this interest. And because we're talking about the long-term sustainability of populated deltas, and that is not always the case. For example, in the tropics, that our deltas, especially in the northern Andes, they are not that populated, but they promise to be very populated. So it is often that the deltas that are not that affected by the climate, the changes that occur in the natural realm, let's say, but they are more affected by what happens with the human alterations, and especially the reduction of sediment delivery, that it's a global change problem, contributes to the sinking of world deltas. So there are hundreds of millions of people at risk. And the question that arises from that is that we have a black box representing the delta system. We have the delta system controlled by the main driver, that is continental sediment flux from the rivers. So we want to know about what is going to happen with that delta, that black box. Especially considering global change, we have a big question of what is going to happen with deltas. It is not as straightforward as we can think of it. So for that, I have to highlight this talk by Yap, made a couple of years ago now within this series, where he presented this global overview of the prediction from boundary conditions, what is happening in the marine realm, with controlling the delta morphology, but from the global perspective, trying to make a statement of what is the not only the prediction of the morphology, but how that comes into the global budget of the sediment that is being delivered, but also sediment that is being reworked at the shoreline. And this relevance of the global view, he presented in the first part of the method that I'm going to highlight today. So I very much encourage you to take a look at that talk. And for today, I also want to highlight these call for papers on prediction in coastal geomorphology. So this prediction that we want to do in deltas, it's very much a topic that is very important today for decision makers to have a a forecast of the of the future state of the morphology where many people is living, and the goods are moved, and also the ecological implications that drive that change in the deltas are very important. So with that, let's say that we have a challenge, and the challenge is to predict the delta shape, how it's going to change from changing environmental conditions, considering global change. That is the challenge that we have and that we want to tackle. So the first part of the talk as such is that framing of the delta shape. So let's consider this, the seminal work by Gallo-way. Professor Gallo-way said, the style of deltaic progression is extremely sensitive to variations in the relative intensity of marine and fluvial processes. That is very important, actually. I highlighted because the key word here is relative intensity, because we have many combinations of that marine and fluvial, and what we want to do is we want to use a framework to predict that delta shape, and to predict it considering those conditions that are changing not only in the continental because of the hydrology, because of the climate, etc., because of how this is changing also the land use, for example, in the continent, but also because of the changes that are occurring in the marine realm. So you all know that the relative intensity can be cast within a dichotomy. The dichotomy is the dichotomy between the continent that is represented here as the sediment input from the river, and the sediment input from the river also encounters at the river mouth, that is here highlighted, that's delta system, what is going in the marine / in a more general sense, the basin that is receiving that river. So that dichotomy is better represented here in this triangle. The triangle is a very famous way of framing that morphology, and it is famous because it gives us a tool to compare, a tool to analyze, a tool to assess what is happening at the delta. So here you all know that or maybe not, so within the Gallo-way triangle, you find these three vertices. The three vertices represent the extremes within that realm, and the extremes are here at the top. You have the fluvial dominance. Here in the left lower vertex, you have the wave dominance, and here you have the tidal dominance. And how it works is that if you have a delta here, you have several shapes, you can find a location within the triangle where the delta lives, and that represents the relative contribution of those three main processes. Of course, the river, but also waves, but also tides. So in other words, if you pick one location, for example, this, you can have this relative contribution for those three within that location. That is going to be different from other location, because, for example, in this case, it is going to be less influenced by waves, and the influence by the river and the tides is going to be more or less half and half, contrary to this location where you have a more influence from waves and from tides, a little bit more from waves, but less influence from the river. So now you may see the potential that we can have here, because of course this triangle didn't have a quantitative framework behind it. It was more like a tool to assess the morphology itself. You can have representations of the relative contribution of each process. You can have the fluvial discharge from the river. You can have the wave energy flux for waves, and you can have a wave energy flux for the tides. but still the quantitative potential, it is not yet fulfilled until you produce or you cast this hypothesis. That is pretty much the hypothesis that Yap developed during his several years of career, and then that ended up with a very high profile publication on this. I'm going to talk about a little bit more on that. And the hypothesis is that you can predict, you can prognose delta morphology if you can quantify the relative influence of the processes, the fluvial and the marine processes. If you can quantify that influence on delta shape, then you can predict the delta morphology within a changing framework of those fluvial and marine processes. That is pretty much our aim. With that hypothesis, we can now enter the realm of quantifying Gallo-way. That is pretty much the nuts and bolts of my talk here. Now, this is from Yap's paper published 2 years ago in Nature, and I know there is some criticism on the way that or the manner that it was applied, this method, but nonetheless it doesn't diminish the credit of the way of finding a way of quantifying this framework of Gallo-way. And here I quote, they introduce a model that shows that present-day delta morphology varies across a continuum between wave tide and river dominance. That is pretty much what we have been talking about with the Gallo-way triangle. And understanding, as they say, the redistribution of sediments by waves and tides will be critical for successfully predicting human-driven change to deltas. So, in other words, if you have this triangle and you can quantify this the relative contribution, you can then assess what is going to happen with the delta in a human-driven change, or considering human-driven change, especially in the continent. So, pretty much, we have to talk about two concepts before we can delve into what Yap presented, and also what we are proposing, and we're finishing proposing, and I'm presenting here in this talk. And the first thing that I have to talk about is the so-called fluvial dominance ratio, and that proposed by Yap also in an early paper, 2015 paper in Geology. And I have to talk about this because keep in mind that we want to find a way of quantifying the relative contribution of the river, waves, and tides. So the fluvial dominance ratio is the ratio between the fluvial sediment flux that is entering a littoral fringe and the maximum wave transport. So just let it sink a little bit, and you may think, okay, why the maximum possible wave transport? What is the relationship within a dominance hierarchy in the delta morphology? And so a good question, or an answer to that could be that if you want to assess whether waves at a particular location have enough, let's say, energy enough, but also the distribution within the wave climate is enough to move the sediment that the river is delivering. So that's pretty much what we want to analyze. Are waves capable enough to move all the sediment the river is debauching? That's the question. So Yap proposed this ratio, and the ratio says, okay, you can have the river flux, and you compare the river flux with the maximum sediment transport move moved by waves. And those are of course, the river is taken from Sagi Cohen's and colleagues, the model, the WBMZ model. I'm not gonna delve into it, but I acknowledge here the reference. And also I'm sticking with the original formulation in the geology paper, but this is pretty much Q River. So we define this as the fluvial sediment flux. And that is going to be divided by the maximum transport by waves. And that transport, we are going to call it Q wave. So pretty much Q River and Q wave. Q River over Q wave. If you divide those two, you can have a sense of the capacity of waves to move sediment compared to the sediment flux. So we can see this here in this image. This is an image from Google, of course, from Google Earth, from the Grijalba Delta in the Gulf of Mexico. And here you have our reference shoreline. So we introduced this concept of reference shoreline that is pretty much the shoreline that we will have if we don't have any delta at all. And at that reference shoreline, you can see that we find a river mouth. And the river mouth, or where the river is debouching, on top of that, we have a wave climate that is pretty much moving sediments there. So that reference shoreline is very important or it's a concept that is helpful in understanding this maximum wave transport capacity. So you have the wave climate, and this is the representation of the distribution of the waves that are occurring in that particular location. Remember, we are going after the maximum transport by waves. So we consider the distribution of the energy, and then that distribution of energy, it's not the same. You have the combination of wave height, but also wave period, but also the wave direction that is here represented by phi, not theta, I'm sorry, but by phi sub 0. And now if we apply this with what we know how waves transport the sediment, that's pretty much the work by Andrew Ashton and colleagues working on how waves transport sediment, sand, especially waves transport sand at the shoreline. You find this distribution that is maximum at an angle close to 45 and minus 45. So that means that if you have a reference shoreline, you can, that an angle at 0, the waves approach the shoreline at an angle of 0, they will have 0 transport. And if they approach the shoreline at 90 and minus 90, they will have a transport of 0 too. And the maximum transport is going to occur at 45 and minus 45. So we combine these two, and we can end up with what is going to be the transport at a particular shoreline with a particular wave climate. And you may say, okay, and how that comes into the maximum transport. And a good answer could be, if you have the distribution of your waves at your location, you can have the maximum and the minimum transport. And the difference between those two, that is going to be pretty much the range of that transport, is going to be your maximum. That is going to be your Q wave, in other words. That is the difference between the values here at this triangle and the value here and this triangle. It's the absolute value, of course. So you have this Q wave from the maximum and the minimum. The minimum is going to be the maximum negative value, and that is going to be your maximum wave at this particular location. Notice that I don't have the actual delta. I am not comparing the delta itself, what is happening at the actual flanks and the actual morphology. I only focusing on the reference shoreline and how the wave climate can play on that reference shoreline. So that's Q wave for waves, and that Q wave enters the fluvial dominance ratio, the first ratio that we introduced to talk about the quantitative Gallo-way framework. Now we have to introduce, or I have to introduce, or reintroduce, because this is already published, of course, the tide dominance ratio. And the tide dominance ratio in a parallel way, in an analogy to the fluvial dominance ratio, is the comparison between the tidal discharge and the fluvial discharge. In this case, we have to in the original formulation, the Nienhaus and colleagues were talked about the discharge, the water discharge, and then they introduce a way, later on, they introduce a way of considering the sediment flux. But the essence is the same. You compare what the tides can move to what the river is debouching, what the river is delivering to the coastline. And here I put the equation, and I know that is not, I'm not making the, I'm trying to explain this fast. So the fastest way to explain this is that this is a representation of tidal prism. So it's a way of connecting sediment transport, a way of with a equilibrium shape within the delta in this case. And I have to make a parenthesis here, disclosure. We are considering delta as everything, every possible morphology that you can find where a river is debouching, is entering a basin of the ocean, a sea, etc. So we are considering there, we have estuarine, alluvial estuaries, we have pretty much the granulated shorelines with in a fluvial dominance delta. You have everything within that word delta. So bear with me in that sense, because I know there are many opportunities to discuss, to explore philosophically that delta term. So I close the disclaimer and keep going. So the Q tide that we have, it's related to the tidal prism. And the tidal prism within a morphodynamic, sediment transport, not only hydraulics, but also morphodynamics. And we use that to represent what the tides can do. And the way we do this, and I take this cartoon from Yap's paper in 2018, it is when you decompose this capacity of tides to move sediment at a coastline, you end up with a relationship that is very important. The relationship is the relationship between the channel width, where there is no tidal influence at this point, so at this location, and the channel width, where the tidal influence is maximum. And that relationship is what we go after when we talk about what tides do to deltas. And that relationship is here within this funnel-shaped cartoon delta. And here you have also the possible relationship between the river and the tide discharge, not only in space, but also in time. So in a space, you have a realm of dominance between the river and the tide, and in time you have this variability in the tidal discharge. And people that do the estuaries, they could say that this is not fair, and the tides do more things than that. It is not a simple sinusoid. It could be a combination of constituents, etc. But we are aware of that, and we try to, in the simplest way possible, we try to represent that relationship. But in essence, we want to connect that comparison between the river, the fluvial flux, and what the tides do here, that's making sediment go back and forth with the tendency of creating this funnel-shaped delta. So lastly, the last thing that I have to introduce before I go into the ternary diagram is the relative sediment flux. That is perhaps the most recent contribution in this sense. And the relative sediment flux is actually the way of connecting the Gallo-way triangle with the processes that we have at A delta. So the relative sediment flux is, if we can define it as or it is defined as the relation between each sediment flux, waves, tides, river, compared to the total sediment flux that is going to be the sum of these three. So pretty much an equation could be like this, where the x could be river or wave or tide, and then you can find a relative sediment flux for the river, and this here is going to be the Q river divided by the sum, etc. And actually, this relative sediment flux allowed us to quantify the ternary diagram. This is Yap contribution, and this is where we try to construct further. And the way it works is that that is something like, if you have this ternary diagram and you have a way of quantifying the relative contribution for the river, for the waves, and for tides, you can go back to the diagram and find that, oh yes, the dominance for rivers is going to be, of course, towards this end. The dominance for waves is going to be toward this end, and the tide is going to be towards this end. And we actually can assign each axis to that relative variable that we just defined. In this case here, you can define these axes or assign the relative wave sediment flux to this axis, where the maximum is 1 for the relative sediment flux, the minimum is 0. Now we also can do that for the relative sediment flux for the tides, and here you can have the 0, and here you have the 1. And the same for the fluvial sediment flux, where you have 1 here and 0 here. So you have 3 axes that work together, because behind the expression, you find that these values, they are combined, and they go from 0 to 1, but they go from 0 to 1 together. They are not independent on each other. So that gives us a way of quantifying the location within each of these axes that combine they give out the location within the triangle. So pretty much that makes us the possibility of, boom, creating this type of diagram that is the contribution by Yap, published in Nature in 2020. And note that we have the relative values here assigned to each of these axes, but also note that the R and the T, the fluvial dominance factor and the tide dominance factor, are pretty much are the values along those axes. They are not within the triangle, but you can locate those values within the axis. And what actually you can do is you can plot virtually all deltas in the world here and see how they compare to each other. And this is the work by Yap, figure number 1 on the paper. And you can find each dot is a delta. You have roughly 10,000 deltas here. And you also have deltas organized by the fluvial sediment flux, and not only by color, but also by size, the marker size. And every single one of them is located within that quantitative framework of Gallo-way. So in other words, you can find one dot here and that dot is going to have as associated a river, R wave, and R tide. And that's the power of this wave of quantitating Gallo-way. You can assign the relative fluxes as a sediment balance problem, and you find yourself linking that sediment balance to the delta shape. Now, this is the way we do it. You calculate the relative Q wave, you plot it here, you go constant along the way. So any point along this line is going to be 0.20, 0.30, and then you find 0.2 here for the relative Q river, and every single dot along this line is going to have that value of 0.2, and then 0.3, 0.2, and then you have the 0.5 here for the Q tide, relative Q tide, and every single point along this line is going to have that 0.2. Now combined, you find that they have an intersection, and that's where our delta lies, or our delta lives. And of course, the sum of those three must be 1, and that's one of the beauty or the simplicity that this approach has to make this work. You have this sediment balance, relative sediment balance of 1, and if we go back to what Gallo-way was proposing in the first place, was that relative contribution of each of those processes, and that represented by the factor that those three combined sum up to 1. Now, what we want to propose now is we want to quantify fluxes, but so far we can't quantify fluxes from the boundary conditions. We have a theory that Yap developed uses boundary conditions for waves and from tides to quantify the fluxes that we expect at the shoreline. But now what we want to do is we want to go and assess the delta morphology, measure the delta morphology, and quantify the fluxes that are related to that morphology. It's kind of going backwards. So first we go from fluxes to morphology. Now we want to go the other way, because the morphology is what we observed, observed in our satellite images, what we observe in the field, and it's pretty much the actual delta that has been built. So to do that, we go back and think, what are the ways we calculate the fluxes? And this is I know you may be thinking, what in the world is this delta doing within that basin? And I know it's a challenge to understand. That is the Atrato Delta, the Atrato Delta in Colombia, in the northern Andes, and that's the Gulf of Urabá. And if we have this delta, it is upside down. The north is in that direction, I know. But if we have that delta, a priori we say that is a fluvial dominated delta, it's a river dominated delta, it's a crenulated shoreline, you have a lot of distributary channels. So we go back to the dominance ratio and we say, when you have the dominance ratio greater than 1, you will expect that fluvial dominance is going to be higher, or the higher the R value, the higher the fluvial dominance. And that's represented morphologically in the number of distributaries. It's very simple. It's how much sediment the river is debouching, the river is delivering, compared to the capacity of waves to move that sediment. So if it is larger than the capacity, you will end up producing more distributary channels, because the sediment must go somewhere, and the way it go, or the fate of the sediments is to produce more channels to redistribute the sediment in several mouths, so the waves can have the chance to try to move the sediment. And if that doesn't happen, well, you will end up creating more distributaries. So what we say is the number of distributaries is pretty much roughly the same as the number of the fluvial dominance. Now we go back and we move, or we put that the other way around, is that we observe a fluvial dominance by counting the number of distributaries. Very simple. But with that, we can have an observed Q wave from the morphology. It's like, what is the Q wave needed to move the sediments that we have, or virtually that we have represented in several distributaries at a delta. So that's the first thing that we want to do. It's the simplest, and it is that the number of distributaries that we count in the field is going to be our actual fluvial dominance ratio. Of course, that is not. It is saying that the fluvial sediment is distributed in a homogeneous manner. That is not true. We know from studies from other colleagues that is not true. That the sediment doesn't distribute in a homogeneous manner. The two distributaries, it means that the sediment is going to be 50%. We know that doesn't work that way, but we also know that we are trying to make a first order prediction here. So bear with me. This is the first thing we do, and going back to our reference shoreline at the Grijalva in the Gulf of Mexico, now we have this. We have a crude river that is debouching, but also we can calculate the actual sediment transport by waves, because we can calculate the angle of the flanks with respect to that reference shoreline. And we do this here in the other. We can do that for a cuspate delta, but for this delta we cannot do that. So what we assume is that at each mouth, the R value is 1. At each mouth, the R value is 1. So we assume that at each distributary in a fluvial dominated delta, waves transport at the maximum capacity, but for that particular location, and that the fluvial sediment flux at that location is going to be equal to that maximum capacity. Now, if we go to this delta, this is the Magdalena Delta. The Magdalena Delta has a backstory, like a very, very important backstory in terms of human interventions, but we're going to just be blind to that right now. We're going to just take a look at the morphology that we find. And if we find this type of morphology, cuspate morphology, you will find that, or you will, a priori, you will say, yes, the fluvial doesn't have enough sediment, so the waves move more sediment that the river can debauch. And that expresses itself, that relationship, in a shoreline protrusion. You have a protrusion that with respect to a general trend, I'm just trying to put in here a priori, you find that the delta has this type of morphology, plane view morphology. So when we compare that, you can predict that protrusion using algebra, linear algebra, with the QNet that we have calculated with the shoreline, with the generalized reference shoreline, and with the wave climate, of course, compared to what the river is debauching. And there you can propose, and this is what we propose, we can have an observed fluvial dominance by comparing that Q wave with what we observe at the delta. So this is the maximum capacity, and then we compare that to what the delta is actually moving. And by that I mean, if we go back again to our reference shoreline, and we have the wave climate, with that wave climate, we can find this unitary from the theory, and you can find, of course, this maximum, but also you can find the actual angles at which the flanks are. And with that angles, you can find the actual transport that you would expect for that particular delta. So in other words, you can have these, the actual transport that you would expect with the wave climate that you have at a location, but also considering the morphology, the left and the right flanks at the delta, because it is a cuspate delta. We cannot do this for a fluvial dominated delta, but for this type of deltas, we can do that, and we can measure the angle, and the angle here and the angle here. They can give us the actual transport, and the transports away from the mouth, they compared to the actual river, what the river is delivering, gives us a sense of how efficient the delta is in moving that sediment that is being delivered to the basin. Of course, we have a way of formally calculating this, but it's pretty much what is the expected in transport at the right flank compared to the left flank. Okay, lastly, we have to talk about tides. This is the San Juan Delta in the Pacific of the Northern Andes, and this is a very special delta. I consider it as being mixed with the mixed dominance. You can see it from the a priori morphology. You can see the barrier islands trying to build, but also you can see the widening of the channels, and you can see that has several distributary channels. So this is a good example of a mixed dominance a priori from what we can assess. But the tide dominance, we already know that it is related to this what we call it a gradient in the channel that we can predict using the tide dominance ratio and the factors that we can calculate from the tides at a location. But so we can go back and express the tide dominance that we observed from the morphology that we measure. So this is from the field. So it's pretty much, we are just going back and modifying the expressions so we can measure the morphology and express the tide dominance ratio. In this case, that it's tide dominance ratio is going to be related to, of course, what the tides are moving and the river is moving. So here we have the example. The example is in the San Juan Delta. You have the Q River here. We have this dotted, this dashed line that represents a profile across the delta, along the delta, and then we have several mouths. You have several distributary channels. I counted here 7, and on top of that, you have the tidal constituents here. You have what we can get from the Topex model from colleagues, and here we have the representation of each constituent by the amplitude and the frequency. Now, this is combined with the delta slope that gives us a way of assessing the hydraulics of the tides, but also of the river. And combined, we can find that the Q tide, what we observe is that dominance that we observe from the morphology, comparing the actual channel width with the combination, hydraulic combination of the channel widths that you have here when you have for example, in this case, a tide dominated delta that have several mouths that combined are larger than this mouth of the river or the channel width of the river. So we can calculate this observed Q tide. So in essence, what we are presenting here is a way of connecting that dominance, not only the fluvial, but also the tide dominance, with 3 main morphological expressions: the number of distributaries, the shoreline cuspate angle, and the channel widening, and that they basically vary in this sense. You have the R values, very small. You have small R values, so you have a shoreline angle of 0. That is pretty much a wave-dominated delta. You have a shoreline, a straight shoreline, and a spit that is preventing the river to go just directly to the basin. And then you have a change in that R. If it increases, the shoreline angle increases up to a maximum where it becomes undetermined. And then here, that is the value of R equals to 1, where you have fluvial dominance, and you start building more distributaries. That is, of course, connected to the number of distributaries, that when R is 1, it goes from 1 to a number of distributaries depending on the delta. You have 14 roughly for the Atrado that I mentioned. You have roughly 200 for the Mississippi Delta. On top of that, you have also the channel widening, and the channel widening is you have small values. It means that you have the river is debauching a lot of sediment compared to what the tide can move. So pretty much the channel width at the mouth is the same of the channel width upstream at the river realm. And as long as you start to increase that tidal discharge, you start to increase the channel widening. So this combines to the, or can be combined into that quantitative triangle, and you can find a way of you can find a morphological expression for each of those realms within the triangle, and then you can assess whether your predictions are close or far away from the observations, not only in terms of the fluxes and the relative fluxes, but also in terms of the morphological expressions that I mentioned. So for example, we have here a prediction of 10 kilograms per second for the river, 15 for the wave, and 25 for the tide. And then we predict the location that will be here. And with those locations, we find these 3 morphological expressions. We have a 1.6 widening, 20.5 degrees of shoreline angle, and 1 distributary. And the observation that we find is 1.3 in the channel widening, the 25 degrees in the shoreline angle, and a number of distributaries of 1 that translates into these fluxes. And then we can assess with a distance within the ternary diagram if those two compare well or not. So this is pretty much what we can have. We have this power to compare the prediction from the boundary conditions to the observations. So now the novelty here is that we can quantify fluxes from morphology within that framework that was already proposed. So some applications, just to wrap this talk up, bringing the work by Seibold and colleagues that is published in the Proceedings of the National Academy of Sciences, where they just pretty much create deltas out of nowhere, let's say, with, of course, considering the theory of the sediment balances. And of course, although there are opportunities for improvement in the way that the deltas are created from nowhere, let's say, they make a very powerful statement that is the shapes in the classification of Gallo-way can be reproduced if you can vary the model parameters and the initial conditions. So you have the pattern structure that is being in good agreement with the real deltas. So in other words, we have now a framework that we can compare to original deltas. And we did that. We have roughly 31 deltas distributed around the world, but then we focus on the North American and South American deltas. And here, the locations, of course, we calculate the relative fluxes, and these fluxes come from the predictions that we have. And we predict, of course, the Mississippi to be up here. We predict the eel to be down here. We predict the copper and the Mackenzie here. We predict the Grijalba here. That, of course, is a Cuspate Delta, should be around this location, more dominated by by waves and the river, but less by the tides. But if you consider the Columbia, for example, you would expect from the predictions to be more tidal dominated. Now, for the South American deltas that we have here the prediction for the Amazon, that is a fluvial, there's just fluvial and tide dominated of roughly 0.5 between those two. You have these, the Paraná Delta here, up here, because of the several, perhaps because it is shielded, and our models cannot show very well what is happening inside the Rio de la Plata estuary. But interestingly, we have these northern Andes deltas here clustered around the predictions are clustered around between the wave and the fluvial dominance. Now, how it compares to the observation, we give some corrections. From the observations, we can see, for example, that the Mississippi should be even further up. We can see that, for example, the Grijalba should be more wave dominated, like go a little bit lower, or at least that from what we present, and the Hill even more lower, like even more wave dominated. Now, for the South American deltas in the northern Andes, we have some interesting things. I mentioned the deltas in the Pacific, the San Juan, this one that I have been showing, but also the Patia and the Mira deltas. They are located here, and I'm very interested about this because they are close to the center, and close to the center is the combination of the fluvial, the tides, and the waves. And you can see that in the morphological expressions. You have channel widening, you have several distributaries, but also you have at the mouths of each of the mouths, you have these sediment spits. You have these spits trying to close the mouth. So you have that combination. But there is one that is very special because of in terms of the global change, that is the Magdalena, and the predictions for the Magdalena are down here. It means that from the morphology, the Magdalena should be, or it is completely wave dominated. And you may say, if you know the Magdalena, you say that the sediment transport is relatively high. But also waves are very important there. You have a narrow shelf, you have waves there at the Caribbean that are approaching the delta, but still there is something fishy going on with the Magdalena. And let's see how do they look, those predictions and the comparison with the observations with the actual values. Here, this is the Mississippi, nothing very striking. It is the classical fluvial dominated river with a lot of distributaries, don't have a cuspid angle, and the error is actually very low from the observations compared to the predictions. Now you have the São Francisco. São Francisco, it's the delta in Brazil. And then you find a relatively larger error. And the error here shows us that you have a cuspid angle. We measure 20 degrees and a widening. We don't find channel widening. And that gives us that 20 degrees, they gives us a little bit more or a lot more of wave dominance according to our framework. And now we have the Magdalena. The Magdalena shows one distributary. And the cuspid angle that we find is roughly 40 degrees, 30, 35, 40 degrees. That's a lot of a large angle. But when you compare the error is relatively large. And we don't, in the case of these errors, we compare the observations with the predictions. So the predictions, of course, they have space for improvement in several areas, but they shouldn't be that different. And my colleagues that know the Magdalena, they know that the engineering projects here, they make the channel width constant. The delta cannot change its shape there. So what we see with this comparison, especially in the Magdalena, that has a large impact by deforestation, like roughly the deforestation, the sediment load is increasing historically. Just from the delta morphology, comparing within this triangle, this quantitative way of quantifying the delta morphology, predicting it and observing it, we see that the morphology is telling us that the controls on the Magdalena make the fluvial sediment to not stay at the delta. And that has been found by other colleagues, but the power of this is that we compare those two. Maybe we can deduce sediment retention if we compare the observed fluxes with the predicted fluxes within that ternary diagram quantitatively. So in essence, we compare the fluxes from morphology and from boundary conditions with the framework. And with that, I have these conclusions that is pretty much what we have been talking about. We want to predict delta shape for evolving environmental conditions. We quantify sediment fluxes from morphology within the framework. And then if we have now with the fluxes from morphology, we can compare those with the predictions from boundary conditions for waves and from tides. And with that, I thank you all for your attention, and I'm open to any questions if we have time for that.
Thank you, Pani. This is fascinating, although I must say that I've heard some of this, familiar with some of it, but and also really nicely on the hour. So any questions? I can think of a couple, but if there's anyone with some questions, please feel free to go ahead.
Hey, Penny, maybe I can start a question. That's fantastic talk, as Yap said. This give such a detail, of course, with wonderful foundation of Yap and laid out. I think you did extend his work. That's great. And the main question here is try to predict the delta shape. Then when we talk about delta shape here, I think you mainly refer the subaerial part.
Yes.
Right? And, but of course, the delta itself is not only the delta plane, not only subaerial portion, there's a big portion is delta front, even the pro-delta. We haven't really talked about it yet because it's not easily observed. And, the subaerial part, you can do a satellite image, but the subaqueous part, you have to do survey. And this is something I think our next couple of years, we can try to put them together. We have already collected so many data about the subaqueous part. We haven't really put them together. And this is the first comments. The second, related to this is, I know, the Gallo-way tried to weave river tide, but to decide the delta shape for the subaerial portion, the geological setting is an important factor. For example, the San Juan River, you talk about discharge to the active margin Pacific. If it discharged to Gulf of Mexico, even a same river flux with a tide, there will be different shape. Yeah. Or Mississippi River, if we let it discharge to the western coast of South America, that would be very different. So I think for geomorphology point of view, that could be another big factor to consider.
Yes, I agree. I totally agree. It's one of the things that I like to I'll start exploring is that actually the geological framework, and as you the example that you put is beautiful because it is exactly that. If you put this San Juan Delta that is that the tectonic framework is so characteristic, and you have these destructive forces as Professor Juan Restrepo has done since the 90s, and there are a couple of good papers on that by Juan, of course, and you put the same input that in the Gulf of Mexico, as you mentioned, of course you will have a different delta, and I find a couple of reasons for that. And the one is that the waves are going to be, even the same waves, they are going to transform differently, and they are going to end up with a different capacity for transport at the very shoreline, because you will have a different submarine slope. The pro delta is going to be different, and actually we have seen this in some work done in the Pacific coast, in the northern Andes. The waves are behave different because the continental shelf control, the width controls how waves transform, and that of course is going to enter the how we predict the deltas. And yes, I agree, and in part I would say that our simple approach has perhaps the elegance. I'm not saying this in a cocky way, because this is actually from Yap's work. The elegance of this simple approach is that the morphology, that's one of our hypotheses, that if we have the delta and the subaerial plane view first order morphology, it's in one way or the other. It's because it has these controls operating on them, on how the processes are shaping the delta. So it is not explicitly considered, but we believe it is implicitly considered, because I don't think the framework is going to be. I believe that the delta shape is going to show that control. So. But yes, I would love to. Actually, that's on my calendar, on my to-do list. I have to run those simulations and with different, just to see with different geological frameworks. Let's say different profiles, just to see if we can expand on that hypothesis. But thank you. That's beautiful. Yeah. Yes.
Yeah, I have a kind of a question / comment, and I fully agree, Paul. I'm just wondering how much of it is a reflection of time and how much of it is a reflection of a different environment, right? If Mississippi were to enter the Pacific, then just creating mouthbars would also just take a lot longer than it would in the Gulf of Mexico. So given enough time, what would you develop? And would you eventually develop a river dominated shape? Would you never develop one? I don't know. So that's why it's like, I don't know. It's perhaps a question for any of you, or I don't know. It's something to think about. And again, if there's no one else, thank you again, Pani. This is wonderful, and I'm very happy this is also on YouTube for my students and for other people out there who wish a thorough introduction into the topic.
Yeah. But before you guys go, I think this is for future. Is there anybody in your group run a Delft 3D to do all that kind of different scenario simulation?
Yes, I'm working with people. Also including Doug Edmonds and Effie Fufula Georgiou, who have an NSF grant to do put Delft 3D simulations into the Gallo-way triangle. So this is currently in revision at GRL. So hopefully it will be out soon.
Very important.
Yes.
When we meet in November, I show you something I did. It's Delft 3D stuff.
Oh, cool. Yeah, it would be nice to see that too.
Yeah. And other question for both of you, and because you already have a good database globally, delta, and you can further categorize them. Some delta may be still in earlier stage. Like a Wilson cycle. The Wilson cycle, when we talk about tectonic, stage 1, stage 6. Delta also show that kind of similar life cycle. Some is a very early stage, still developing juvenile stage. Some in the middle age. Some already mature, already reached the equilibrium. And even the rivers keep dumping sediment, but because of geology, because of oceanographic regime, so it's not progradating anymore.
Mm-hmm.
And some of course, because maybe decline, because cut down the sediment, that could be eroding. So maybe something we can, further do, twist around of your database, have that kind of stuff.
Yeah, that would be nice.
Yeah,
it would be good to see if we can perhaps also quantify the tectonic regime between different deltas and see if we can detect some patterns.
Yeah, I have some, when we talk, we can talk about more, that some delta definitely already reached the mature stage. Some already show is a decline. Some is still growing like a young man.
We have several deltas here in that juvenile, let's say, state, and they are in very challenging tectonic settings, and I know that they could be a very good data set to test these ideas. And several comes to mind. The problem is that we don't have a very good data set, like geophysical data set for the small deltas, only for the large deltas. So that will be a challenge, but definitely something. Yeah, we have a very good laboratory here in the Northern Andes. So yeah.
Fantastic.
All right. Well,
okay.
Thanks again, Pani, and see you in a couple of weeks.
Sure.